Okay, so you should have these two figures folded up, and they won't stay, and that's okay. We don't really want them to stay. But these two nets make two what? Prisms. Okay, so the blue one is what? Rectangular prism, and the yellow one is a triangular prism. Okay, so it kind of looks like it might even be more of a specialized kind of triangular prism. What does this triangle look like? Equilateral triangle. So it may be, it may not be. It doesn't really matter right now. But you could have something that says that it's an equilateral triangular prism, and that's telling you that the base is an equilateral triangle. Okay, but at the very least, it's a triangular prism, and we know that much. Okay, so we are going to start with, so this piece of paper that I gave you here, I want you to go ahead and fold it in half because it's going in your ISN. This one is going on page 97 when we are done. There's not a space for the ISN page, but go ahead and put 97 on there. And then going to open it up. All right. Now, one of the things that we have to remember about all of these, because it's one of the things that's going to get you in trouble if you're not paying attention to it, is which shape the base is. So for the rectangular prism, which one is the base? Any of them, because they're all rectangles, right? And if we find volume, it doesn't matter if you and I choose a different base. If we find total surface area, doesn't matter if you and I choose a different base. Lateral area, though, would be different. Well, it could be. It could be the same by coincidence, but it's most likely going to be different unless it's a specialized kind of prism. So for purposes of being consistent on your homework for lateral area and just stuff like that, we use what it's sitting on as the base only if it's a rectangular prism, because technically it could be any of them, but again, we're just trying to be consistent. So we're going to glue this down by its base, which again could be any of them. I'm just going to tell you which one it is just because so it'll fit on the paper. That's why there's little outlines here. But before you glue anything, I want you to lay it out so you know that this right here, this rectangle, and it doesn't matter which side you put out the lines or not. I'm going to do this so you can see the lines. This one is the base. And so make sure it's going to fit on your paper without hanging off or anything when you glue it down. You are not gluing this entire thing down flat because that would make absolutely no sense. All right? But all you're going to do is put glue right in the rectangle itself on the piece of paper. I made this so it would be really easy for you to do. And you can even see my glue because it's purple. So I'm just putting it in the little rectangle, and then I'm gluing it down like so. Okay. All right, so with it glued down, I can build my three-dimensional figure like this and see what's going on here, and then I can flatten it out and keep it in my ISN, and it's kind of like a little pop-up book, okay? I don't know that the prism part of this is going to be as helpful as the rest. Like, I kind of feel like you don't necessarily even need all of this for the prisms, but we're going to do it for all of them just so we can hopefully make it all make more sense. So when I lay it all out, I'm going to label these pieces here. So this one that we glued down, this is the base. And it would help if you could actually see what I was writing. So hang on. There we go. And so this is big B, right? Big B is the base. So which one of these other rectangles is the other base then? The one on the far right, because when I build it, it's the one that's going to be parallel to it, right? So this is also big B. But on this one, I want you to write it on the outside too, so you can like flip it over, and that way when it's built, you can see it as well. We want to be able to see it in the built form and in the net form, right? So these are the two bases, and then as the net, where's the height? This, like this right here, right? Because we want to always think of the height as what? The distance between the bases. So the distance between the bases right here, this would be the height, this would be the height, right? And then on this rectangle right here, top, bottom, left, or right, which one of these sides would have the same length as the height? The left and the right. Because when you build it, you see how those match up? So this would have the length of the height also. Plus, when you build it, it is the distance between the bases. So we're going to put H's everywhere there's the height. And then we want to do that on the outside too. So if I just take this right-hand side and I just flip it down like this, I just flipped it all the way over so I could write it on the outside. That's the height, that's the height. And you can turn your paper if you need to. And I can do the same thing over here. And then I can do the same thing for these. And I'm going to turn mine around so that it's not upside down when I actually build it. Got a little carried away with my glue there. H. If you write them upside down, they kind of look like Y's. But when you build it, you see where big B is, and you see that the height is the distance between the bases, which also in this case happens to be how tall it is off of the paper, because we glued it down on the base, but that's not necessarily always the case, because you can even find the height when it's in the net form, and that's not how tall anything is. It is literally the distance between the bases. Okay, we all good? All right, so this is a what? Triangular prism, right? So I'm going to take this and we're going to glue it down by its base. But again, go ahead and lay it out flat and make sure you're putting it in the direction where it won't be hanging off of your paper. Should just fit right in there. Then I'm going to put glue in my triangle. And then I'm going to glue my triangle down. All right, so this is a triangular prism. What is the base? The triangle, because it is a triangular prism, right? So when it is laid out flat, I'm going to label that this is big B and this is big B. And then the height is the distance between the bases. So this is the height, this is the height, this is the height. This is the height. Then I also want that on the outside, so I'm going to flip it over this way so I can label this as big B and then the height here. That way when it is built, I can see that that's big B, the height is the distance between the bases, and then check this out. Even when I take this and I lay it down, I can lay it down and still have the prism because I can pretend like it's closed over here. The height is still the distance between the bases. The height is not how tall it is off of the paper. Does that make sense to you? We good? Okay. So everybody okay with all the prism stuff? Yes? All right. So then we're going to fill in these formulas from yesterday. Lateral area for a prism is going to be LA equals what? PH. Capital P, lowercase h. There were two different forms of the surface area formula depending on what we're asked for at what time. I could have surface area equals lateral area plus 2 times big B. I would use that if I already found the lateral area, right? Or I can have surface area is equal to perimeter times height plus 2 times big B. Those are really the exact same thing, just something substituted in. You could use either one of them at either time as long as you find all the right stuff. Okay, we all good so far? All right, so we're going to pause on this. We're going to go to the notes and talk about a few things over there, and then we're going to come back to this and talk about the cylinders. So we're going to kind of go back and forth today on these. So here, this is going on page 96 when we're done. And we're going to talk a little bit about cylinders. Okay? So, a cylinder. This is no surprise. We even talked about it the other day. I know you know what a cylinder is. It's a three-dimensional figure with 2 parallel circular bases, I left off a very important word here. What did I leave off? Up to that point. No, up to this point, what did I leave off? A cylinder is a three-dimensional figure with two parallel circular bases. What do they have to be besides just circular? Congruent, yes. So add congruent, and I left that off. Congruent circular bases and a curved lateral surface that connects the bases. Okay, there's your cylinder. Is a cylinder a polyhedron? No. Okay, so the curved surface that connects the bases is called the lateral surface. Okay, that's the lateral surface, the curved part. So then, come down here and look at these pictures here. So you've got this cylinder, which looks like a cylinder that you're used to, right? And then you've got the cylinder that's leaning over. So this one is a right cylinder. What is the other one called? Oblique. Good. So you got a right cylinder and an oblique cylinder. Everybody okay with that? All right, so then what goes in this next blank up here, the blank, blank, blank is the segment with endpoints at the centers of the bases. So this red dotted line that I have here and here is the word that we're trying to define. Now, in the right cylinder, what could this represent that we already know about? The height, okay? Which the height is the length. The segment itself is called the what? Altitude, okay. But would it, in the oblique cylinder, represent the altitude? No, okay, because they're different. Does that make sense why it's not the altitude in both? So I need something to be able to refer to it as that would work for all cylinders, whether they're right cylinders or whether they're oblique cylinders. And it's because it doesn't have to be perpendicular. All it does is connect the bases. And so it is the axis of a cylinder. There actually needs to be another little blank in there, but axis of a cylinder. So this here, even though it does represent the altitude there, this is the axis, and this is pointing to it as well. So you can just kind of extend that so you don't have to write it twice. These lines are pointing to the lateral surface. You might want to extend those as well if you need to. These represent the bases, and so do these. When you draw a cylinder two-dimensionally, do the bases look like circles? Like, does that look like a circle? No, it looks like an oval, right? But that's just because it's a three-dimensional figure drawn on a two-dimensional plane. So they're circles regardless of whether or not it's oblique. When it leans, it doesn't squish the circle and make it an ellipse or anything. It's still a circle, even though I know neither one of them look like it. All right, so these three, the axis of a right cylinder, okay, so if we know we have a right cylinder, then it is perpendicular to its bases. The axis of an oblique cylinder is not perpendicular to its bases. And the axis of a right cylinder is the same length as the height. And we already talked about that, but everybody good with all that? Just the pieces of a cylinder? Yes? All right, so let's look at this last question down here. It says, after looking at the figure above, is the axis of the cylinder always the altitude? Why or why not? Is it always the altitude? No, because the altitude is always what? Perpendicular, okay? So the answer is no. Altitude is always perpendicular to the bases. Technically, it's the planes of the bases, but same thing, really. Everybody good with that? Any questions? All right, so before we move on, I'm going to give you another net. Be careful with this. I had somebody cut all these out for you so that you didn't have to do it, because we really just didn't have the time to do it. I've never had somebody cut them out for me before. So don't let the little circles fall off or rip them off by accident. Okay, so in order for me to get these to fit on the paper, I had to reflect them. So different people may have these that fit on the paper differently. I'm not even sure that I have one that I could. Yeah, I got two. So do you see how, like, if you look at the black lines on these, oh, dang it. Like the circles are in a different spot, which is fine. It just is going to change how you would fit it on the piece of paper. You can fit them like this, and it doesn't matter if the lines are inside or outside. You could make it fit like this. Just because these little sections here are a little bit different on each one, you might want to make sure that you lay it out before you decide how you want to glue it down. Okay, so lay it out on your paper, figure out, it doesn't matter, as long as it fits and it's not going to hang off your paper, it doesn't matter, and then you can glue it down. Okay? However it works for you. I'm going to do mine this way, I think. And then if yours is turned differently than mine, again, which is fine, you may have to write in a different spot on the paper than I am, but it's all good. Okay? So this is the net of a what? A cylinder, right? So once you've got that, technically this circle would only touch that at one little point, so we have to cheat a little bit or it's just going to fall apart. But go ahead and, once it's glued, build your cylinder. Think about what you have here. And although a cylinder does not have any polygons on it, its net does. Right? Its net has a rectangle. How many of you have never really looked at a net of a cylinder before? Anybody? A few people? Okay. Does it make sense that this is a rectangle? Think about a label on a can. If you slice the label and unroll it, isn't it a rectangle? That's how the labels come out, and then they just wrap them around, right? So we've got this as our net for our cylinder. So for a prism, big B, the shape of the base could be any polygon. But for a cylinder, the base is always a what? Circle. So this is big B, okay? But because it's always a circle, I can be more specific with my big B formula, right? And that big B formula would always be what? Pi r squared, right? It's always pi r squared because the base is always a circle. And so the radius is always important to us in a circle. Now, this part right here represents the lateral surface, right? And so the lateral area would just be the area of this rectangle. And we know how to find the area of a rectangle, right? It's just base times height. So I've got to think about what those pieces would be here. What does this right here represent in my cylinder? The height, because it is the distance between the bases, right? The base of the rectangle, this whole part right here, what does that represent from the cylinder? Circumference. And if you didn't know that or didn't make sense, that's what happens when you wrap this around. Doesn't that length right there just wrap around your circle? This has to be the same distance as the distance around your circle. So it is circumference, which is 2 pi r. Everybody good with that? Now, if you have an actual label on a can, most of the time that length would be a little bit more than the circumference because they want a little bit of an overlap. But when you're just building a cylinder itself, then it's the exact same measurement. So here's the thing about cylinders and prisms. And I talked yesterday a little bit about how some of us are formula people, most of us probably are not, and we don't want to have to understand, and it's not a memorizing thing, understand and learn 1,000 different formulas. So you can use the exact same formula for a cylinder that you did for a prism, right? They have very different properties, but really the formulas still work. What's the lateral area formula for a prism? LA equals perimeter times height, right? Right, well that works for a cylinder, but what's wrong with it for a cylinder? We don't really have a perimeter, right? I mean, the perimeter doesn't exist, but what do we use in place of the perimeter? The circumference, okay? But the nice thing here is I don't have to use a capital C in my formula, because here I had to use a capital P, because the perimeter could be found a bazillion different ways, because we don't know what the actual, how many sides the actual base has for any given prism until we get there. But for a cylinder, it's always the same. The perimeter is always the circumference because it's always a circle. So instead of P times H, I just substitute that, and the LA equals 2 pi R times H. That's just the base times the height. That's all it is. Thank you. Does that make sense to you? So when you get confused, because after we get some other formulas, some of y'all are going to be like, I don't know if it was 2 or if it was squared or what was happening. If you just think about it as perimeter times height, you should know what's supposed to actually go there. Okay? Does that make sense to you? The more you can relate things to each other that actually relate to each other, the easier of a time you're going to have being able to process it all and make sense of it. Okay? We good? So on this one also, I want this stuff on the outside. So in order to do that, I'm going to flip mine upside down so that I can then flip it this way. So I can label a height, circumference, and this is big B, which is pi R squared. So that way when it's built, I can see that same thing on the outside, because you can't see what you did on the inside. So for cylinders, our lateral area, we just came up with it. Lateral area is equal to, we can use perimeter times height. I mean, that works, right? But really, the better thing to do is lateral area equals 2 pi RH. You will never see this version on a formula chart for a cylinder, because that's not the official formula. This is the official formula. But again, this one works, but this is the one that you would, really use if you know what it is and can get there. So for surface area, you've got really 3 options here. You can use this one right here. This one straight up works over here. Lateral area plus 2 times big B. That one works. Okay, we're not going to write it down though, so we have room for the other ones. But I can also do lateral area, no, not lateral, I'm sorry, surface area, dang it. Surface area equals, well, if I already have the lateral area, I don't need to find it again. So lateral area plus, but instead of 2 times big B, my big B formula is always pi R squared. So 2 pi R squared. Or let's say all they asked me for was the total surface area, and I didn't find that yet. I could still use this formula and go find it. Or I could say that the surface area is 2 pi RH plus 2 pi R squared. But again, if this is all I know right here, all of this can totally be applied to the cylinders if you know how to understand how to do it right. Okay, we all good with that? Any questions? Okay, so you want to carefully, bless you, make sure that these are flat so that you don't destroy anything, and then fold them so that you don't mess anything up. And then we're going to go back over to the other notes and finish those up. So we've already come up with this stuff, so we're just going to write it down. This is what we just came up with on that other page. We came up with the fact that we can use lateral area, bless you, equals perimeter times height. That works, but that's really for a prism. So really what we should be using is lateral area equals 2 pi RH. There is your lateral area formula. I can use surface area equals lateral area plus 2 times big B, because that works. I mean, that's just very generic. You just got to go find the pieces and put them in. I could have surface area is equal to lateral area, if I already have it, plus 2 pi R squared. Or if I got to do it all at once, surface area is equal to 2 pi RH plus 2 pi R squared. Okay, so really, these two are the ones to choose from. Then over here, we'll label this as H. Big B is always equal to pi r squared. This is the circumference, which is 2 pi r. This is the height, and this is big B. The height is hard to see. So that's really the same thing we had on the other paper, but on the other paper we're going to have them all together and go back and add volume when we get there, but I want this on these notes as well. Okay, we all good? Any questions? All right. So we're going to find the lateral area and surface area of, surface area of the right cylinder. Okay, and notice it says up here, I didn't point this out, that lateral area and surface area of right cylinders. So these formulas do not work for oblique cylinders, okay? We would have to do something else, which we're not going to get into. So this is only right cylinders. So we're going to find the lateral area and surface area of the right cylinder. So to start with the lateral area, I'm going to do 2 pi RH. All right, so did they give me the radius? No. Did they give me the height? Yes. Do I know the radius by looking at this? Yes. What is it? 8. Very, very good habit to get into. Write down what the radius is. I know it's easy. I know you know what the radius is. Have you ever used the diameter instead of the radius or vice versa? Yes, most likely at least once in your life. Some of you probably a lot. So that's a really easy mistake to avoid by writing it down. But sometimes we write it down and we still use the wrong thing because we're human. So substitute it in 2 times pi times the radius, which is 8, times the height, which is 10. So my lateral area then is 160 pi inches squared. Easy enough? So of the 3 surface area formulas that I gave you, I'm thinking that the second one probably makes the most sense here, right? Because I already have the lateral area. So surface area is equal to lateral area plus 2 pi r squared. So that's going to give me 160 pi plus 2 times pi times 8 squared. So what's 8 squared? 64, and then 64 times 2 is 128. So I get 128 pi there, which means in the end my surface area is 288 pi, which is squared. Easy enough? Any questions? All right. All right, so let's look at the next page. It says, find the surface area of the composite figures. So I want you to look at this first figure, and what I want you to do before we do surface area or anything else is I just want you to think about and come up with a plan. Okay, like what would you do? We got to find this and do this or whatever, but come up with a plan and write down a plan right here of how you would do this. Okay, I'll give you a second to do that. All right, who wants to give me one version of the plan? Anybody? You want to do it? Okay. Okay. Minus 2. Okay. What do you think? Y'all agree with that? Yes, no, maybe? Okay, before we talk about that, anybody want to give me a different plan? What you got? Okay. And then plus or minus anything? No? Okay. What do you think? Anybody have anything different than those two? Okay, so let's talk about this. I have some visual aids here if I don't drop them all over the place when I'm trying to use them because I'm not that coordinated. Okay. I've got this, and it's not going to look exactly like that, but it's kind of the best I could do. Got my jalapeno can in a box. So it kind of looks like this, right? So I could find the total surface area of both. And if I find the total surface area of both, I have this and I have this, right? When I put them together, there's a problem, right? Because I can't get from inside the can to inside the box. Yes? So if I subtract one circle, I can take the bottom off the cylinder, right? So I take the bottom off the cylinder, that's open, but I still have a problem with the box, right? I'd have to cut a hole in the box to be able to get from one to the other. Does that make sense to you? That's why you subtract two, because there's two layers when you stack them together. Make sense? Okay. And one of the reasons that I'm using these kinds of things instead of, fancy, cutesy math stuff is, first of all, I hate spending money on that kind of stuff, even when it's not mine. But second of all, when you're at home, like this is a really cool cone that shows you all kinds of conic sections. Do y'all have these at home? No, even I don't have one at home, okay? I know y'all think I have like stuff like this on my mantle, but I don't. I don't have this at home. So it's not going to do you any good if this is the only thing you ever see. So if I have some other fancy thing to show you this, you don't have that at home either. But do you have a box and a can where you can like put it together so you can see it and think about it? Like you just find stuff to make it make sense to you, okay? So does everybody understand why the first one works? Yes, okay. So does anybody think that the second one doesn't work or not understand why it works? That concept, that way of thinking about it is harder for some people. That's more like a building it from scratch instead of putting it all together and taking stuff away. So what that one says is the surface area of the prism and just the lateral area of the cylinder like this, right? So if I put those two things together, I have two problems. I don't have a top right here, plus I can't get into the box, yes? But when I cut the circle out to get into the box, isn't it going to be the same size that goes right here? So basically, it's just like moving that piece from there to here. Okay, so those two processes get you the exact same thing. Which one you use doesn't matter. Okay, one is not always shorter than the other. Sometimes they are, sometimes they're not. It just depends on what's going on. But shorter isn't always that important when you don't understand what you're doing. So if you can't wrap your mind around the second one, it's okay. Everybody needs to understand how to do the first one for sure. If you prefer to do the second, I am totally fine with that. But if you can't even wrap your mind around the first one, then that's going to be a problem moving forward. Are we good? Yes? Okay. So now I want you to look at the second one, but I got to talk about the picture just a little bit because the way these pictures are shaded, that it leads you to misunderstanding how some of this stuff works. Oh, I wanted to put or. You could have either one. And you don't have to write them exactly like I do. I mean, I just don't want to write out all the words, but that's literally a little equation. After I find everything, I go back and I do that, all right? Okay, so here. What is happening here? Because it's not shaded well, and I'm not capable of fixing it. Even if I was, I still don't know how I'd do it well. But what this is a triangular prism, and it has a cylinder going through it. It's like a tunnel. I know it doesn't really look like it's open there, but it is, okay? So I could step inside of this tunnel and walk through the cylinder and walk completely out the other side. Okay, does that make sense to you? So I want you to think about that. Come up with a plan to find that surface area. While you're doing that, I'm going to hand out the homework. And then I'm going to hand you something else to help you with it. All right, who wants to give me something? Somebody that hasn't been giving me anything. Anybody? Give me something. Give me something. Give me. That's okay. My guess is whether it's right or not, somebody else is thinking the same thing. So just give me what you got. Surface area of the prism, okay, and the what now? Lateral area of the cylinder. And what do I do with them? Adam? Okay. Okay, that's okay. What, do you have something different? Okay. Oh. Okay. And then that's it? Okay. Anybody have anything different? Okay. I'm going to give you something else. All right, I need this back, and you're gonna have to share these, and don't lose my little pieces. I made these with sponges from Walgreens and an apple core. So you have to share them at your table because I don't have enough for everybody. Do I have to subtract? So you're saying surface area of the prism minus the lateral area of the cylinder? No? Minus the two bases on which one of these? The second one? Minus two, what bases of what? Okay, so this is why you don't want to put like minus 2 times big B, because you got bases of different things, right? So if I meant the prism, I'd put a triangle probably. If I meant the cylinder, I'd put a circle, something like that. Okay? Anybody have anything different than that? Okay. Surface area of the prism minus two bases of what? The cylinder. Okay. And then what was the last part? Okay. Add the lateral area of the cylinder. Okay. And then subtract 2 circles. Okay. So these are very similar except how many circles we subtract. Anybody think we're supposed to subtract the lateral area of the cylinder? Okay, that's good, because that's usually the first thing I get, and I have to have a really hard time convincing people otherwise. That's why I gave you these things, right? When you take this sponge that was started full, and you take out that cylinder, I subtracted a cylinder, right? But I added more surface area. I have less volume here, but more surface area. Does that make sense to you? And that's hard to wrap your mind around at first. That's why I gave you this thing. So we're going to pretend like it was purple, and we painted it all blue. So when I take this out, you see how I have to add more blue paint to that cylinder? Because I actually now have a cylinder in there I didn't have before. You with me on that? So yes, we're taking a cylinder out, but there's really no subtraction of a cylinder anywhere. So the main difference between these two, this is like taking the prism and putting the cylinder together and just cutting out 2 circles. This one is the prism. We add just the lateral area part and take away 2 circles. So these both can't be 100% right because they both subtract 2 circles, and these things here are different. Which one of these we can edit a little bit and it'll be fine, and one of these is correct at this point. Which one do you think is correct at this point? The one with the lateral. Because if I have a box, which I don't have one of those, but if I had a triangular prism box, and this was actually solid in here, right? And it was like, empty. Then I put the cylinder, the lateral area in there. I'd have to cut holes on either side to be able to walk through, right? Here, if I take a box that's an empty triangular prism, I put in there like a Pringle can, right, that fits on the ends. And then I need to be able to walk through it. If I just subtract 2 circles, am I going to be able to walk through it? No, because you have 2 layers on each end, right? How many circles would I have to subtract? 4. So if I change this to 4, this works. Okay? Does that make sense to you? Now, the way that Kevin said this to me, he said surface area of the prism minus 2 circles plus the lateral area of the cylinder. Is that the same thing as what I wrote? I mean, it's not, well, literally, obviously it's not the exact same thing, but does it end up with the same answer in the end? Yes, but this was like his thought process. I have the prism. Okay, I got to cut circles in the end to open it up. And then I'm just going to stick like a tube in there, which would just be the lateral area. Does that make sense to you? So this is a good way to think through it. Some people think through it this way. This one right here, though, when all else fails, find the surface area of everything, put it together, think about in your mind, how many layers do I have and what all do I have to subtract, and that'll get you to the same place. Okay, because some people will have a hard time with putting just the pieces in there. That's just when things get a little bit weirder. So on your homework, the questions that look like this, if it looks like it's supposed to be a hole, it's supposed to be a hole. All right, I mean, there's just nothing I can do about those pictures. If you have questions about them, you let me know. Okay, we can look at them real quick. So on 3, that cylinder goes all the way through. It's like a bead or something. And then that's really the only one that's really the only one that goes like that. All right, are we good? We're going to do a whole lot more of these, so you got to practice and get your mind wrapped around it, yes? All right, so put my little sponges back together for me. I'm going to come around and get those.